All right, so as we mentioned earlier, next week will be the exam. So for this lecture, I'll dedicate a little bit of time toward the end. Basically, like one half of the class on two things: review session, and let's discuss about your project. If you from what we gather before we start the lecture, it seems like everyone is trying to see what would be a good idea for the project. So let's brainstorm about that toward the second half of the class. Now let's go to the next set of material, to be honest, that I would like to cover, which is the memory, full-blown memory that we kind of skip over and assume that these are the magic thing that would gather your data and send it back to the CPU, right? So today we will learn the basic. I'll go over the material that if you're in a computer science or computer engineering program, you're supposed to know these things already from undergrad. But even if you're not from the program, or if your program in Thailand is not featuring a decent undergrad ComArch classes, which might happen, right? You might have seen this concept and then kind of forgot about it and then actually doesn't really understand what they are. I want to give you a brief overview. I want to then quickly go over. I would assume that you've at least seen some of this before. If you have not, right? If you have not, please let me know on Discord. I have a much longer video that I used to teach the undergraduate students at Mahidol University, which I would recommend, right? It would allow you to kind of dive deeper into the foundation of the concept and why does it work, and also how does it work, all right? I want to do this so that we can kind of follow through to the second half of the class where we discuss more of the design issue with memory. Right? Things that we kind of like a post undergrad level. Okay, so if you are the programmer, right? And if you program in Python or Java, you're like basically dealing with this magic memory where you allocate a variable and somehow you got the space and everything prepared for you. There's no such thing as memory allocation. If you look at C or C++, then you might be dealing with memory allocation, malloc, right? But even then, when you have this API calls from the system that allow you to say, hey, I want more space for my data, and they'll basically give you, here is a pointer that points to the space that you want, right? Free land, right? The thing is, from the programmer view, that's nice. In the abstraction level, right? Programmers see that I can always ask for more memory. The worst case is I use too much memory and then you slow down. Your computer gets slower, but that's it. It doesn't really crash my program, if you will, right? I also should see the memory to be a contiguous thing. It's a long, continuous blank space that you can use, right? Imagine you allocate an array, right? Let's say you have an array that is, let's say 100,000 in size, right? It's an integer array, for example. You would imagine that every single items here are next to each other. It literally should sit next to each other. But I mean, imagine, let's say you run, how many people have their desktop or laptop open for at least a week? And you haven't restart or shut down. How many of you are using your laptop like that these days? Please raise your hand. Raise my hand too, right? Because that's a fact. We designed the computer in such a robust way that I don't have to reboot my computer at all. I just put it to the sleep mode and then come back. Windows is there. I don't have to restart Windows, right? But if you think about it, it means that every running program, basically they pause and rerun when you come back, right? Now, how many programs and how much memory have all these programs been using on an aggregate manner in a week? let me rephrase that question in Thai just to make sure you understand the conceptual of the problem and the motivation behind it, right? ก็คือถ้าสมมุติเรารันโปรแกรมแบบ10 โปรแกรมไปเรื่อยๆวีคหนึ่งนะคือแต่ละโปรแกรมก็จะใช้ที่ของมัน เสร็จแล้วพอมันใช้ที่เสร็จก็คืนพี่ครับคืนครับ แล้วก็ขอที่ใหม่ตรงนี้ คืนที่ตรงนี้ขอที่ใหม่ตรงนี้ ให้นึกสภาพว่าสมมุติเมมโมรีเราอ่ะคือพื้นที่ทั้งหมดในกรุงเทพใช่ไหมสมมุติเมมโมรีเราคือพื้นที่ทั้งหมดในกรุงเทพแล้วบอกว่าเฮ้ยโปรแกรมนี้มาแล้วขอใช้ที่ตรงตรงสีลมโปรแกรมนี้มาขอใช้ที่ได้ที่ตรงสาทรโปรแกรมนี้มาบอกขอใช้ที่ได้ที่ตรงบางแคโปรแกรมนี้มาบอกเอ้ยผมใช้ที่เสร็จแล้วคืนที่ส่วนหนึ่งในสีลมก็ถูกคืนกลับมาที่รัฐบาลก็คือ OS แล้วรัฐบาลสามารถเอาที่ตรงเนี้ยที่คนอื่นคืนมาเอาไปให้คนอื่นใช้ต่อได้ ปัญหาของเราก็คือถ้าผมทำอย่างเงี้ยผมจะได้พื้นที่ที่เป็นแบบจุดโล่งๆแต่ว่าที่เล็กๆเต็มไปหมดหรือเปล่าก็คือมีคนขอคนคืนคนขอคนคืนเพราะฉะนั้นผมก็จะได้แบบการแบ่งโซนที่หน้าตาประหลาดมากๆเพราะว่าบางทีผมขอที่ขนาดใหญ่แล้วผมคืนที่อัดกลับมาเป็นอันเล็กๆก่อนอันเล็กๆก็แบบตอนเล็กๆแล้วเพื่อนเดินเข้ามาบอกผมขอที่บ้างแล้วก็คือ มันก็จะเป็นที่ผมสลับกับที่เพื่อนสลับกับที่ผมสลับกับที่เพื่อนแบบมั่วๆไปหมดเนี่ยนึกภาพออกไหมฮะถ้าเราเปิดคอมไว้วีคหนึ่งอะแรมมันจะหน้าตาแบบนั้นมันกระจายไปหมดเลยคือเมมโมรีของเราอะที่เราใช้อยู่ในโปรแกรมอะมันจะอยู่แบบกระจายทั่วไปหมดเลย so the problem is from the programmer point of view, right? You basically want things to be contiguous and your array should be next to each other. But in reality, if you open your computer for a long time, there'll be allocation, deallocation, allocation, deallocation. That array might be partially here and partially there. And there's like some weird gap in the middle that's used by someone else. But somehow from the programmer point of view, you still see that two chunk of space as one continuous array. All right. Again, recap this in Thai. ก็คือสมมุติผม declare array ขนาดใหญ่ๆอย่างเงี้ยอ้วนๆขนาด100,000 ตัว ถ้าเราเปิดคอมมานานๆไอ้100,000 ตัวเนี้ยเราอาจจะไม่มีที่พอที่จะบอกว่าเฮ้ย100,000 ตัวมันใหญ่มาก ที่ของคุณน่ะไม่พอ คอมมันก็จะบอกงั้นครึ่งหนึ่งอ่ะ150,000แรกอยู่ตรงนี้แล้วกันนะ50,000ที่2อยู่ตรงนี้แล้วกันนะ แล้วระบบของคอมพิวเตอร์มันจะทำให้แบบว่าจากโปรแกรมเมอร์ที่เห็นอ่ะทั้งก้อนเนี้ยที่มันอยู่2 ก้อนสองส่วนที่ไม่ต่อกันอ่ะจริงๆแล้วแต่โปรแกรมเมอร์มันจะคิดว่ามันต่อกันอยู่ แล้วเราสามารถใช้งานได้เหมือนมันต่อกันอยู่นะครับอันนี้คือการ manage memory ของคอมพิวเตอร์ที่ทำให้เรา why do we do this? Basically, it's make your life easier. It's make your life a lot easier. You do not have to worry about who else are running on my computer, right? I only have to worry about your own code, which is already enough, right? If I ask any programmer that say, hey, do you want to worry about someone else's code that are running on the machine? Everyone will say, no, I want to just look at my code and debug my own code and move on. All right. No one, you don't want to fix someone else's problem. Okay. And inside the hardware, please also then be aware that the main memory is physical, right? So here's what you want in the memory. I want them to be fast. Zero latency means that I want my data and somehow the data arrive right away. Unlimited capacity. I want my memory to be as big as possible. I want them to be free. I want them to have a lot of bandwidth. I can send a lot of parallel memory requests to the memory. But obviously, that's impossible. It's too magical, right? All of these will conflict with each other. I want a fast memory is probably be expensive. I want a lot of memory is also going to be expensive, right? I want a lot of memory is also will make your memory potentially slower. Imagine you have to search for someone in a big auditorium versus a smaller room, right? You can find your friend in a smaller room much, much quicker. So a big memory is going to be likely a little bit slower than a small memory, right? There's also multiple types of memory technology. The first type you see on your CPU, these are on your CPU, is called SRAM. SRAM are fast. The idea of SRAM is I will build it based on 6 transistors, where 2 will be used as a NOT gate. Another 2 will be used as a NOT gate. So these are 2 transistors here, 2 transistors here. You see it basically loop around. It traps the electron. So when you want to store the data, it traps the electron in here. Then you have the access transistor here and here, right? One more. So these are called access transistor, which allow you to basically access the cell, read or write to the cell. These are really fast. Really, like basically 1 kilobyte of SRAM will be as like almost as fast as 1 add operation, which is like 3 or 4 cycle. It's taking basically less than 1 nanosecond, right? So if you read the spec sheet, most of the time the L1 cache is going to be revolving around 4 cycle or 5 cycle or 3 cycles, which is really quick. Then you can have a bigger cache, right? We use these as a cache, which is a concept we can learn today, right? So a bigger cache would take a few more cycles. It could be like 15 cycles, 20 cycles, depending on the size. Then you have DRAM technology. DRAM is, you can think of it as, I use capacitor. So this is a capacitor. Capacitor is a circuit component that allow you to trap electron. You can store electron in here, that's ground, right? And then over here, you have another transistor to do the access, right? Transistor to do the access, all right? And the idea is I use the transistor essentially as a switch. So if you will, this thing, the transistor here, think of it as a switch, right? You open and close so they can access to the cell. So in an abstract sense, this becomes a switch, right? Over here as well, you have a transistor that is essentially a switch that you can connect and access the cell, put electrons in or leak them out. A gigabyte of DRAM is going to be something like sub 10 nanosecond, and the number is a little bit older. Do you say you're looking at maybe something like 10 nanosecond, which is still really, really, really long, right? Or if you're unlucky, you might have to wait in a queue to be serviced by DRAM. We'll talk about this technology in a few lectures, all right? But in that case, you're going to basically spend 100 of cycle, like 50 nanosecond. That's like 150 cycle for a 3.3 gigahertz clock. A long time. Recap. SRAM, small but fast. DRAM, big but slower. All right, that's it. DRAM is what you call the memory when you buy a computer. We also cover emerging memory technology like 3D stack DRAM and tiling later on in this course. Also NVRAM, non-volatile RAM, which kind of work more like an SSD that are really, really, really fast. They are not like we use basically right now you cannot buy a device that do NVRAM, but it's likely to be something that might come into the market in a I'm pretty sure within the next 10 years. It will make your DRAM much, much big. Basically, not your DRAM, it will make your memory a lot bigger. All right. So here's the question. SRAM is fast, but expensive and also small. DRAM is cheap, but it's basically high capacity and slow, right? I want to be greedy. I want everything. I want to be able to support a lot of memory, but for most of my data access, I want them to be fast. So here's the idea. I will have a hierarchy of memory. That's why we call this memory hierarchy. So think of it as, let's say you're hungry at VISTEC right now. I'll use this example every single semester until you guys have a legit town around on your campus. All right. So let's say you're hungry. What are you gonna do? One. What's your option?
Walk to the cafe, Amazon.
Walk to cafe Amazon. How many of you have like a snack in your lab, just in case? What's the KKN?
ครัวคุณนกครับ
Oh, Kurokunok. Okay. Possible option, right? How many of you also? Oh, okay. I visited your campus before. I saw that at least, like, for example, Advanced Saranat Lab has like the coffee table, right? That you can at least make coffee. And many of you have like snacks or like whatever on your desk or in somewhere in the lab, right? Think of the lab area as like your cache, right? The lowest level cache, the L1 cache. If you are hungry, that will be the first place you walk around and look at. Are there anything in here I can eat except your friends or the computer? Don't do that, all right, folks? But like, are there snacks or things you can eat? Then, if you cannot find any food in the lab, also don't steal someone else's food. Then you call Croconut or go to Cafe Amazon outside of the building, right? So you walk around to get some. Well, Cafe Amazon is basically coffee or light snack, right? How long would that take? I think maybe like 5 to 10 minutes, right? So when you access your own snack, goodbye my L1. Oh, okay. You have side channel attack. I would call that side channel attack. Someone else modifying your cache data from something to nothing because the ants are there. All right. Basically, it corrupts your data. You cannot really access L1. But basically, you can imagine, like, let's say you have a snack in the lab, right? And then that be your L1. If you want something more fancy, let's say you want coffee, right? Your lab, oh, actually, you have a lab. Your lab has coffee. So let's say you want something like a sandwich, right? Then you can go to Cafe Amazon, which should take longer. You have to actually walk quite a distance to the place, right? So it would take longer, but the benefit is they have more items. You can buy more things. They have a lot of snacks, right? I believe also nearby 7-Eleven. So think of it as the same thing. They would stock a lot of things, right? But let's say you want something else. You want something fancy, something that 7-Eleven or Amazon cannot give you. What's your option? Any nearby restaurant that you can maybe drive through? Pistanavan. Okay. So again, treat L1 as like your hidden stash. Sorry, I don't know why I'm writing stack twice. Hidden stash that you can store your food in the lab. All right. And then treat the L2 as the Cafe Amazon, right? And if you think about food, I guess 7-Eleven, which is further away, will become your L3. But it's still on campus, right? It's not bad. Treat your Jiffy SPT, yeah, treat these as like things on your VISTEC campus, right? So you don't have to go out of your campus. Treat that as these are things on your CPU. If I need the data, it's still in my CPU, right? Then your DRAM is when you have to go outside of your campus to a restaurant, right? So this is like a off campus, right? Okay, and then this is basically the concept of memory hierarchy. If you have the disk, for example, let's say you open too many Chrome tabs and your memory is full, your data will be bounced off to the hard drive. Treat that as you need to drive all the way to Bangkok to get food, right? So that's how far things are in a relative sense. And literally, it might be, even if you want to use the actual comparison, it will likely be way further than Bangkok. It might be like VISTEC to Chiang Mai or VISTEC to Korea in terms of going to the hard drive. That's why when your memory is full, it's going to be really, really slowing your computer down, right? Then if you have a network drive, most of the time when you have, in a relative sense, when you think about the time it takes to go get those type of data, right? It's a different granularity for sure. But in that case, you're looking at something like maybe you have to fly to like the United States to get food or something like that, right? Oh, 7-Eleven is closed. I'm sorry to hear that. Well, at least I have Jiffy. I'm not sure. I am trying to encourage you, but I cannot. I run out of idea. I'm sorry about that. Yeah. So here's the memory hierarchy. You have the CPU core. Then most of the time in your CPU, you have this. Somehow we call it private L1 cache. So each core has its own L1 cache. Then you would basically, whenever you need data, the first place you check is the L1 cache. Then if you say, hey, your data is not here, then you will go to the L2 cache that's shared, right? And I like the hidden stash analogy, like your hidden secret pocket of food in the lab, that's yours, right? It's private to you. That's your L1. If you cannot find it, you can go to like Cafe, Amazon, which everyone can go to. Then if you cannot find whatever you want, then you go to the main memory, which is like a restaurant nearby. All right. Now today we will talk about caching. Okay, we will just focus on caching. Then we'll follow after the midterm with DRAM, how it actually works. Okay, so caching basics. It's kind of like basically the idea take advantage of two things, right? The first thing is temporal locality. The key idea is when I write a program, for example, if I write a loop like this, for I equals 0, I is less than n, I plus plus, right? And then I want to access array of I, and I just say a of I equal to I plus 10. How many times in this loop that I am going to access the variable I? A lot, all right? I will access the variable I all the time, actually, all the time. And that makes sense because that's actually the nature of how you program, right? That's how you program. So in this case, I would call that the variable I, I'm sorry, the variable I has high temporal locality because you're basically using it all the time. The idea of caching is to keep this data as low as possible by putting in the L1 cache. We want them to have low latency. This is an idea that's been proposed for a long time, right? Morris Lucas basically kind of came up with the paper in an attributed transaction electronic computer called slave memory and dynamic storage allocation that kind of like basically proposed this design, right? How many years ago was that? Close to, wait, I cannot do math, like 60 years, right? Close to 60 years, just 58 years ago, we came up with how to put data we use often in the cache, right? Then another paper coming 3 years afterward, right? That talk about the design of the System 360, which is one of the prominent system back in the day. It's one of the prominent data supercomputer back in the day, I guess. It's like a really high performance system back in the day. The idea is if you use the array A this way, you are basically accessing A0, then you access nearby component A1, then A2, right? Then A3. So the way you program means that you will have what we call spatial locality. You access something close to them. To remember this, temporal is time, spatial is space. So time, you use it again. Space, you use something nearby, all right? To manage data in the cache, you can do it manually. That's an option if you want to use the GPU software managed cache. You say, hey, I want to put this in the memory, right? It's painful for the programmer, especially if you don't want to think about it. There's so many other problems that you're programming to think about, right? So the alternative solution, which is everywhere in your computer nowadays, is the hardware manage it for you. You do not have to worry about what food you should. Basically, think of it this way. Again, we use a food analogy, right? I will not let you decide what food you're going to start in the lab, in Cafe Amazon, or in 7-Eleven. I will let the hardware decide what goes in there based on your usage, based on your demand. We will try to predict what should be in there. And hopefully we do the right job. This is automatic hardware management of the data in the cache, right? Programmer only just use the memory reference. I have the address and I use the address, that's it, okay? Then you ask this, then why do we learn caching? The thing is, if you know how caching works, you can then write the program that is friendly toward the management in the hardware, right? Write a program in a cache-friendly manner. This is basically one of the classic way in high performance computing and performance optimization. Write a cache-friendly code. It will make your code faster. So the idea behind caching, the basic terminology is if you recall the load instruction when you want to get the data from your DRAM, each instruction takes in one word. One word can be 32-bit or 64 bits, right? Caching also has its own unit of data. We call this a cache block, and it's much bigger than one single data access from your CPU. A cache block, for example, in the CPU is 64 bytes, which is bigger than the typical data load, right? The cache block will be mapped somewhere in the cache, all right? And the access is going to be to a certain part of the cache. Think of it this way. Now I will change the analogy, all right? I will change the analogy from getting food to you go to a movie. Everyone here has been to a movie theater before, is it? Everyone here has been to a movie theater, right? Once you got the movie ticket and you walk into the theater, let's imagine that theater as the cache, okay? Let's imagine that theater as the cache. What do you look for in terms of finding your seat? How do you find your seat in the movie theater? Do you search everywhere for that one chair? Or what do you do first? You have the seat level, right? The index will show you that two things you will see. The letter and then the number. The letter represents the row and then the number represents the seat, right? So the first thing you do is go to that row. The same concept apply for the cache. The first thing the cache access do is where is the row? We call this the cache set. So what is the set that we want to check if we have the data or not? Basically, for every single address that your program use, it will be mapped to a certain cache set, or if you will, using the theater analogy, every single data asset is assigned a row. So when you want to check if the data is there or not, you don't search the entire theater, you search just that row. Is that going to be faster than searching the entire theater for your seat? Definitely faster, all right? So when your load or store want to look up the data, basically we call it a cache hit. if the data is in the cache, and a cache miss if it's not in the cache. And now here's a design choice, right? What to store in the cache? Do you store instruction? Do you store data? Do you store virtual address translation data? We will talk about it later, okay? The second design choice is how do we place the data in the cache? And when the cache is full, how do you pick what to remove, okay? And also how to deal with the write when there are many processors that want to access the data and there are many layers of the cache. Should you manage the cache in a smaller or bigger granularity? So here's a primitive cache design. A cache consists of the tag store and the data store. Let me first explain the data store. This is basically your data. It's as simple as that. That's your data, right? Then the tag store, imagine that is a seat number and the row number. There's your ID, like that match your theater ticket, essentially, right? So in the theater scenario, the tag store is the seat number. The tag store is a seat number. It also includes things like a valid bit, which is either 0 or 1, right? 0 or 1. 0 means that this is just a junk data. Don't take it. Even though you think you map here, that's not the valid data. It's not yours. 1 means, yeah, that's your data. Use it. It's a valid data. There is also the dirty bits and the LRU bit. We'll talk about this too later. This has to deal with writes and also has to deal with when the cache is full. What do we do to kick things out? Okay, so those are the tag store. Basically, you use your, basically the data address, the address is then used as an index to search the tag store, right? So what's in the tag store? As I said, there's tag, there's a reception policy, the valid bit, the dirty bits, right? We talked about this, some of this already. The tag is used to search for the entry. The rest we'll talk about it afterward, okay? The organization is a cache will contain multiple cache blocks. Each of the cache blocks belong to a cache set. The memory address is going to be mapped to a certain set. This, again, using the theater analogy, cache set is the row, cache block is the seat number. Okay, cache set is the row, cache block is the seat number. So first thing you do, check where is the set. Go to that set, then you search your tag for the correct seat number. Okay. And here's more like a visualization of the cache. Let's imagine in this case, you have the cache that contains 16 cache blocks. Let's say each cache block is 64 bytes. It means that the total size of these particular cache is 16 multiplied by 64, right? So that's 2 to the 6 multiplied by 2 to the 4 is 2 to the 10. So that should be basically 1 kilobyte cache with 8 set. Again, use set as analogous to the seat row, the row in the theater, right? So in this case, it's a theater where there are 8 rows. Each row has 2 seats. Okay. Each of these seats are cache blocks. Your data can be in one of these cache blocks. To look up, the address is basically divided into, divided into multiple set of bits. So let's say this is your address, right? And let's say your cache block size is 64 bytes. This basically means that to get to the exact byte that you want to access, you will need basically, once you identify your seat in the theater, once you identify the cache block, the next thing you have to do is to use the lower ends of your address to say which byte you're trying to access. So the last few bits is going to be used to what we call the byte in block. We are searching what byte in the cache block so that we can do the access we want. This is going to be, the size of this is going to be log2 of the cache block size. So let's say the cache block size is 64 bytes. This means that this is going to be from bit 0 to bit 5. These bits, these 6 bits will represent what byte we are trying to access in the cache block. This is byte 0. This is byte 63. Are we accessing byte 0? Are we accessing byte number 7, byte number 13, byte number 23, or byte number 63? We use this part to determine that. All right. Then the next set of bits, we will call them the index bit. So let's say your cache has 8 sets. It basically means that your index bit need to be able to go from 0 to 7. 0 to 7. Again, let's imagine that 8 rows in a theater, right? You basically need to make sure you have enough bit to represent row 0, row 1, row 2, row 3, up to row 7. To actually calculate that, right? Basically, we can use the log function again. It's log 2 of the number of sets. In this case, let's say it's 8 sets, it's 3 bits. From bit 6, 7, and 8, these are the index bit. Otherwise, the rest are your tag bit. And again, this is your address, right? The rest are the tag bits. To search, so basically now to kind of formalize what I just explained, to get the index bit and tag bit. The least significant bits are reserved for the byte in the cache line or cache block that you're trying to access. You can calculate the number of bits by log 2 of that. Then the next significant bits are reserved for the index bit. It tells you what set do you go to. Do you go to row 0 or row 1 in the theater? What set do you go to? And the rest are the tag bits. What's the seat number? Okay, if the seat number match, that's your. If the seat number doesn't match, that's not your data. Go search somewhere else. Okay. Then there are multiple types of the cache. The first type is called direct map cache. Direct map cache means that a cache block can go into one single location. Basically, what I mean by this is there's one block per set. For the entire cache, each set only contains one cache block. If you go to the set and something is there, and if the tag match, that's yours, it's a cache hit. Otherwise, it's a cache miss. If it's hit, you return the data. Otherwise, you go to the next level of the cache. Older machine will use the direct map cache a bit because it's simpler to design. Newer machines, not the case anymore. Newer machine, we have the set associative cache, which means that for each set, we have more than one block. Imagine theater again, go to the movie theater. A set associative cache is I have multiple seats in a row. A direct map cache is I have only one seat per row. Okay, so one block per row. Set associative cache is I have n seat per row, n block per set. Okay, so we call the cache basically once you get to your set, then you check the tag. Is that your seat? Is that your seat? Is that your seat? Is that your seat? If the seat number doesn't match, your data is not there. If your seat number is matched, your data is there. This is called set associative cache. For example, if you see the 4-way set associative cache, this means that there are 4 blocks per set. It's as simple as that, 4 blocks per set. All right. The downside is when you found the set, you still have to check where's your seat. It's a little bit slower than the direct map cache, just a little bit. Then you have a fully associative cache where you have one row. Every seat is in that row. Basically, one cache set. You search every single block. You search every single block. Sometimes this works well if your cache is small enough and you want to make sure that I can replace whatever row I want to do. And it can be a bad idea if your cache is really big. Okay, if your cache is really big, basically when you go look at the cache, you search everything, search forever. All right. The next thing we have to discuss is how to insert and replace data from into the cache, right? The direct map cache is simple. There's only one thing in there. If you cannot find your data, then you go to the memory, you bring in new data, you kick the old guy, replace it with your data. Okay, just replace that data in the set. Set associative cache is more complicated because now you have a choice. You bring in a new guy. You have 4 seats. Someone sitting in all the 4 seats. The new guy say, hey, I need to pick who to kick out from this row, right? Again, you have a new cache block. There are, say, 4 cache block in a row already in the cache set. You need to pick who to kick, right? The key issue involves 3 things: insertion, promotion, and eviction. Insertion means that where do we insert into cache initially? Promotion means that if I have the data access to the data in the cache, do we promote them to say, hey, this is the last guy I accessed? Eviction means that I have a new guy coming in. Who do I kick out? It's as simple as that. All right. So that's a wrap. Let's wrap for the like a really preliminary caching. Okay. Next week we'll have an exam. The week after we'll talk about these insertion, promotion, eviction policy in more detail. Now let's do a quick break. Let's come back at 10 minutes past 10, and let's talk a little bit about your project and brainstorm about your project a little bit. We'll also kind of go over the topics that will be, well, might be on the midterm, right? Potentially. Next week is your midterm. It will be, basically, I will release the midterm at 9 o'clock in the morning. You submit at noon. Yeah, that's it. It'll be online, okay? Online, open, everything. Feel free to use whatever. If you want to use ChatGPT, you can do it. Then you need to pick whether that's the correct answer or not, okay? I'll design a question to make sure that you at least need to make the decision on the answer coming from ChatGPT, all right? So yeah, so let's do a quick break. We'll be back at 10 o'clock. No, 10:10, my bad, 10:10.